Hello, I'm Sebastien Durif. I work at the University Clermont-Auvergne. I will present you the work we have done with my colleague Hamid Bouchair and my colleague from University of Aveiro, Nuno Lopes, on the numerical and analytical study of intermediate web post buckling. We observe since a decade a growing use of web openings in steel beams, as it allows passing through different kinds of ducts and thus reduces the flow's depth. For many reasons, we can have either isolated openings or uniformly distributed openings, such as cellular beams. Of course, having multiple large web openings may induce several additional failure modes, and the impact of large web openings is especially important in high shear areas. In those areas, we are particularly interested in two failure modes. The web post buckling at the left and the Vierendeel bending at the right. In our case, we are specifically interested in the web post buckling. However, we will see that this failure mode is very linked to the Vierendeel bending. So first I will briefly present you the main existing analytical methods. Then I will present numerical studies made on two models, a global beam model and then a single web post model. And I will end with a comparison with an alternative analytical approach. Several methods have been developed to deal with the web post buckling, and I chose to speak about the three main models that are used. I have not the time to present all three, but here are the main conclusions that I wanted to share. The previous UNV Annex N proposes a model based on the elastic strength of the web post, using calibrated coefficients. The buckling theory before those coefficients is not clear, and it leads usually to very conservative results. The SCI model, based on the flexural buckling of the compressed diagonal in the web post, considers the flexural buckling of a diagonal supposed to be submitted to an axial stress, which is directly taken from the horizontal shear stress at the web post mid-height, which is a quite important simplification. Finally, the CTSM, which appeared to be the most accurate one for circular openings. However, again, this model uses a numerically calibrated approach, as it calculates its buckling coefficient considering, again, the flexural buckling of an encased base column. This model is the only one also considering a post-critical effect, using a calibrated coefficient which increases the calculated value of the stress resistance. So the main questions on this existing approach is that the Annex N and CTSM model have the problem to be adapted to various opening geometries, as they use numerically calibrated coefficients, especially the CTSM model, which is developed only for cellular beams. The Annex N just is not adapted to fire conditions. And finally, the SCI and CTSM model are mainly based on flexural buckling, whereas there is no axial force, but only shear and bending moment in the web post. Thus, we propose an alternative approach which is mainly based on lateral torsional buckling, which for us is more adapted to the type of internal force and also the shape of the buckling. Therefore, we propose to study and consider also the post-critical strength after the loss of an intermediate web post, just as initiated by the CTSM. So this numerical study will be based on two models, the global beam model at the left and an isolated single web post model at the right. Both models will use 4 nodes shell elements, an elastic perfectly plastic steel material. We made the calculation in high displacement, considering a S-shape initial imperfections. Firstly, we observe the web post in a global beam model. This model is made of a castellated beam composed of 6 openings and submitted to 4-point bending. As a consequence, both openings 1 and 2 are submitted to an equal shear force, and the intermediate web post is submitted to a bitriangular bending moment. The objectives are to observe the failure of the web post and then to evaluate the post-critical behavior of the beam. Here is an example of comparisons between two beams. Both beams are the same, except on the web thickness and steel grade. Indeed, the main objective is to favor instability in the second case, with a thinner web, 6 mm, and a higher steel grade. As a first observation, we have the stress distribution in the critical section of the web post. The first beam at the left shows the formation of a plastic hinge. Indeed, all elements reach the elastic limit and maintain a plastic plateau. In the other case, at the right, we clearly see that after reaching the elastic limit, the most compressed elements start to lose stresses, which coincides with the lateral displacement of the web post. The second case is therefore a typical case of lateral buckling of the web post. Finally, we chose to mark the vertical displacement that corresponds to the plastic hinge or to the local buckling for the other case, which is around 10 and 10.5 millimeters. If now we look at the global behavior of both beams, it can be clearly observed that in both cases we have an elastoplastic behavior. In both cases, the instant of web post failure, around 10 millimeters, does not correspond to the maximum load failure, which suggests a post-critical strength. And now, if we look at the stress distribution at the opening corner close to the web post, it can be observed that as the web post fails, the stresses in those areas remain constant or sometimes decrease. However, for the opposite corners, the stress distribution is very different, with a clear formation of plastic hinge and a slight acceleration in stress distribution after the web post failure. And it can be seen that those plastic hinges coincide more with the global failure of the beam. The first main conclusion on those observations is that the global beams have a post-critical strength, and which corresponds to clearly the formation of a plastic mechanism of an enlarged opening. Indeed, as you know, cellular and castellated beams are highly hyperstatic structures, just like verandel frames, and thus the loss of an intermediate web post should not lead to global failure. In fact, before you have bitriangular bending moments in each opening members. When the intermediate web post fails, a redistribution of the internal bending moments is made on an enlarged opening, which lead to higher bending moments on the extreme opening corners and internal forces that drop to zero close to the web post, which explains the constant stresses that we observed after the web post failure. This phenomenon could be observed for both cases, and in both cases either we had plastification of the web post or lateral buckling of the web post, and both reached a plastic mechanism in the enlarged opening. As we can have either instability or plastification of the web post, it appears necessary to propose a kind of classification. So first I will present the model of isolated web post, which is used for a parametrical study. And this study aims at finding the maximal reduced strandedness value that corresponds to plastic behavior. This relative strandedness is defined as described in Eurocode 3 for lateral buckling, with the square root of the ratio between the critical bending moment and the plastic strength. The critical bending moment is directly obtained via the free software developed by the CTICM, LTBeam-N. Again, this numerical study is made using Sapphire software, using shell elements and high displacements. The web post is considered fixed at both ends and transversally loaded at the bottom flange. This model has the same internal forces than the corresponding global beams and has the advantage of having the same deflected shape, lateral displacements, as observed in global beams without any additional lateral supports. Here is an example of comparison between two web post models, one with a thickness of 10 mm and the other one with a thickness of 6 mm. At the left, a model with a reduced slenderness of 0.379, and at the right, with a thinner web and a slenderness of 0.688. It can be observed that the first web post has a plastic behavior, whereas the second one observes a peak of load followed by a decrease, typical of instability. If we look at the stress distribution, it confirms that the model at the left reaches the plastic hinge, whereas the second model fails due to instability. After many calculations, we could see that the limitations between both behaviors, plastic and instability, is for a reduced slenderness around 0.57. The analytical model is based on the lateral torsional buckling method of Eurocode 3 part 1.1 using the buckling curve D, and the critical bending moment is deduced from the free software of the CTICM LTBIM-N. The differences with the numerical results are calculated as described here. Here are some results of the comparative studies we made. For each case, a stress analysis at the critical section has been made to define whether or not the Webpost buckles, and this is described here by behaviors 1 or 2. And it can be seen that the frontier between both behaviors corresponds to a relative stiffness of 0.57 and 2. The first observation that can be made is that the narrowness of the Webpost is clearly not relevant of the potential of buckling. For example, the Webpost 1 of 6 mm thick and 15 mm wide plastifies, and the Webpost number 12 of 6 mm thick and 150 mm wide buckles. However, it can be observed that the relative slenderness, lambda, is clearly relevant to define the Webpost behavior. As the reduced slenderness increases, the behavior changes from plastic to lateral buckling. Finally, it can be seen that the cases that consider a plastic strength give accurate results. Furthermore, we can see that for the cases 4, 7, 8, 11, and 12, lateral buckling was observed, and the analytical model appears much more conservative compared to the plastic strength. So here is another comparison of all Webposts in function of the relative slenderness, and we compare in blue the values with the plastic strength and in orange with the lateral buckling strength. And we can see that for many, all cases, approximately, the plastic values remain conservative and very accurate results. However, at the end, for very high values of relative slenderness, it starts to be unsafe. On the contrary, the values obtained using the lateral buckling values appear to be rather conservative, and but we still propose to use them after a relative slenderness of 0.57, which is the frontier between behavior 1 and 2 observed numerically. And finally, those differences for lateral buckling can be improved by using a more adapted lateral buckling curve. So, as a conclusion, we could see that the intermediate Webpost can either plastify or fail by lateral torsional buckling. The difference in behavior can be ordered in function of a relative slenderness. Other studies have been made on octagonal openings, and similar observations have been made. And in case of lateral buckling cases, we observed that the model is rather conservative, but we could improve this model by using a buckling curve like the buckling curve A or B. Thank you for your attention.